Let's calculate the expected value of a Poisson distribution. Say the random variable x has a Poisson distribution with parameter mu, and let's show that the expected value of x turns out to be identical to the parameter, e of x equals mu. We begin by writing down the probability function, f of x equals mu to the x over x factorial, e to the minus mu, and the possible values of x, 0, 1, 2, 3, all the non-negative integers. So the expected value of x is the sum over all values of x, 0 to infinity, x times this probability function, f of x. You'll notice that the first term in this sum, corresponding to x equals 0, is 0, because it's 0 times f of 0. Because it's 0, we can omit it and begin the sum at x equals 1. You'll also notice that x times mu to the x divided by x factorial, you'll notice that there's an x in the numerator, and there's also a factor x contained in x factorial in the denominator. X divided by x factorial is equivalent to 1 over x minus 1 factorial. So that's the simplification in the second equation on that line. And in the last line, we've removed a factor mu, rewritten the sum, mu to the x minus 1 over x minus 1 factorial, e to the minus mu, then changed the variable x minus 1 to a variable called j, whose values now run from 0 up to infinity. And finally, we recognize the sum, mu to the j over j factorial, as the series expansion of e to the mu. So we're left with mu times e to the mu times e to the minus mu, which turns out to be exactly mu. The expected value of a binomial distribution. If x is binomial with parameters n and p, we'll show that the expected value of x is n times p. Once again, we'll write down the probability function, f of x equals n choose x, p to the x, 1 minus p to the n minus x. Now the values of x run from 0 up to n, so the expected value of x is the sum over these values of x times n choose x, p to the x, 1 minus p to the n minus x. And we carry out steps much like we did with the Poisson distribution. Removing the first term because its value is 0, discovering that we have an x in the numerator and an x factorial in the denominator, which permits cancellation of the x in the x factorial in the denominator, leaving x minus 1 factorial, taking a constant n times p outside the summation sign, and then discovering that what's left is the sum of the probability function for another binomial distribution, a binomial distribution with parameters n minus 1 and p. So we have n times p times the sum of all of the probabilities for a binomial n minus 1p, and that last object is 1. In other words, we end up with n times p. You should go over these steps on your own. Example, the expected value of a geometric distribution. Suppose that x has a geometric distribution with parameter p. I'd like to show that the expected value of x is 1 minus p divided by p. Once again, we begin by writing down the probability function, f of x is p times 1 minus p to the power x. Once again, the expected value of x is the sum of all the values, little x, times f of x. We pull out a factor of 1 minus p. We're left with a summation x equals 0 to infinity, x times 1 minus p to the power x minus 1. There's a trick involved in evaluating this summation. Notice that if I have 1 minus p to the power x, and I take its derivative with respect to p, this may seem unusual because you're used to differentiating with respect to x. In this case, we're differentiating with respect to p and holding x a constant. Well, the derivative of 1 minus p to the power x is minus x times 1 minus p to the power x minus 1. It's exactly the term which, when added, produces the line above. And the big advantage in taking the derivative of the sum of 1 minus p to the x is that that's the sum of a geometric series. We know what that sum is. That geometric series adds to 1 over p. So with a little algebra, we ended up with 1 minus p over p. Does this make sense? Suppose the probability of a heads on a toss of a coin is 1/3. What's the expected number of tails we'll get before we obtain the first heads? The claim here is that expected value is 1 minus p over p, which is 2/3 over 1/3, which is 2. On average, you should get 2 tails before the first heads. And in this case, that seems natural because the odds of tails to heads is 2 to 1. The expected value of a function of x. Expected value of some function g of x of a random variable, where x has probability function f of x, is defined similarly. We add over all the possible values of x, the value of the function g of x, times the probability of that value of x. It's the sum of g of x times f of x. Here's an example. Tasmanian Devil Safari. The charge for entry to a drive-through wildlife park is based on the number of occupants of a car. The charge is $30 per car, plus $5 for each of the first 4 occupants of the car. But to give larger families a break, they only charge for the first 4 occupants. What's the average charge per car if x has the following probability function? Of course, there has to be at least 1 occupant of the car. That probability is 0.2. 2 occupants has probability 0.3. Up to 6 occupants, which has probability 0.05. The charge applied to such an automobile is g of x, where x is the number of occupants of the car, and the function g of x is the minimum of 50 and 30 plus 5x. Then the average charge per car is the expected value of g of x. It's the sum as x goes from 1 up to 6, g of little x, f of x. Or $35 times 0.2, that's the charge for a 1-person car, plus 40, 0.3, 40 is the charge for a 2-person car, and 0.3 is the probability of that case, and so on. Of course, the last 3 cases, 4, 5, and 6 occupants, all have exactly the same charge, namely $50. Now, when we determine that sum, we end up with $42.75, 42 3/4. You should remember that the expected value of x and the expected value of any function of x, g of x, these are always constants. They're numbers. They're not random variables. They're what we refer to as deterministic quantities. They're the center of a distribution. In some sense, they're the number that best represents the random quantity x or g of x. That's closest to it. This is easy to prove because the expected value of ax plus b is the sum over all x, ax plus b times the probability function. And by breaking that sum into 2 parts, we end up with the sum of a times x times f of x plus the sum of b times f of x. And the constant a can be drawn outside that summation sign to leave us with a times the sum of x f of x. We recognize the sum of x f of x as the expected value of x. So this first term becomes a times the expected value of x. What about the second term? B times the sum over all x of f of x. That's the sum of a probability function, which is 1. That becomes b times 1, or just b. By a similar argument, if I have 2 functions, g of x and h of x, then the expected value of the sum is the sum of the expected values. This is important to remember. It'll be easy to remember. It's so musical. The sum of the expected values is identical to the expected value of the sum. Here's a question you should try on your own. Suppose x has probability function given below. What's the expected value of 2x plus 1/2? By the way, what are the values of 2x plus 1/2 like? It can take possible values 1/2, 2.5, and 4.5. So here are your choices for the expected value of 2x plus 1/2. So the choices are A, 0.8, B, 1, C, 2, D, 2.1, and E, 4. You should pause now and spend a few minutes working this out. We'll use the properties of expected value we saw earlier in this problem. The expected value of x, 0 times 0.5, plus 1 times 0.2, plus 2 times 0.3, which is 0.8. So the expected value of 2 times x plus 1/2 is 2 times e of x plus 1/2, 2 times 0.8 plus 1/2, which is 2.1. So the correct answer is D. Here's another question along similar lines. X has the same probability function, but now we're interested in the expected value of 0.5 plus 5 times 2 to the power x. And we've got a number of choices from A to E. In this example, we can't simply move the expected value into the exponent above 2. We have to compute it by evaluating the function at each value of x and multiplying by the corresponding probability, which is 0.5 plus 5 2 to the power 0 times 0.5, 0.5 plus 5 times 2 to the power 1 times 0.2, and so on. The sum is 11. Here's a game. We toss a fair coin 100 times and count the random variable x, which is the number of heads we obtain. And I'm willing to pay you a function of x. G of x equals x minus 50 squared. This, of course, is marvelous. You could win up to a maximum of 50 squared, $2,500 by this game, when x is either 100 or 0. Of course, I have to charge you a nominal fee for handling, a $30 fee, say, to play the game. But you'll notice that even at that, provided x takes a value greater than or equal to 56, or less than or equal to 44, in other words, in 90 of the 101 possible values of x, you still make a net profit. My point is that it's a very good deal for you, and obviously a very bad deal for me. How much do you expect to gain or lose over time if we play this game repeatedly? I've graphed the profit below as a function of x. You'll see that at either end, at x equals 0 or 100, your profit is $2,500. You'll also see that it dips slightly below 0 when x is near 50. In fact, when x is 50, I suppose, you still have to pay the nominal $30 fee. This quantity is determined by the expected value of g of x minus 30, which of course we obtain by adding up all the values of the function x minus 50 squared, times the probability of those values, given by the binomial probability function, and subtracting off the constant 30. And you can work that out. It's a little complicated as a sum, but it turns out to be minus 5. Indeed, on average, you lose $5 per game, which means, of course, that I make $5 per game. The expected value seems to tell quite a different story than the superficial graph that I've shown you and the arguments in terms of the number of cases. Why? Because the probability of values near 50 is much higher than the probability of values near the extreme where you win a great deal of money, 0 or 100. Here's a doubling up strategy, which is commonly used by gamblers. The idea is this. You bet $1, say, on the heads in a fair coin, and you'll win $1 if the heads appears. You lose $1, of course, if tails appears. Then your expected profit is 1 times the probability of that, 1/2, minus 1 times the probability of that, 1/2, which turns out to be 0, and 0 is quite disappointing. Here's an alternative strategy. I'll start with a stake, a bet of $1, but every time I lose, I will double my stake. This means that if I get heads for the first time on the 5th toss of the coin, then I bet $1 initially, and I lost, minus 1. I bet $2, and I lost, minus 2. I now bet $4, lost again, minus 4. I bet $8, each time doubling my bet when I lose, lost again. So in total, I have lost 1 plus 2 plus 4 plus $8. But finally, on the 5th toss, I got a heads, and I won 16, since that was my bet at that point. And you'll notice that's equal to $1, plus $1. Indeed, your first heads appears after 10 tails. Then your profit is the sum I goes minus the sum I goes from 0 up to 9, 2 to the power I, plus 2 to the power 10. Again, this is $1. Remarkably, no matter how long you have to wait to get your first heads, you always win $1. What an amazing strategy. Where's the catch? How much credit do you require in order to play this game? If x is the number of tails that you obtain before your first heads, then x has a geometric distribution with parameter 1/2. The probability function is f of x equals 1/2 to the power x plus 1. The possible values for x are 0, 1, 2, all the non-negative integers. Then your debt before you finally win is a function of x. It's the sum I goes from 0 up to x minus 1, 2 to the power I. We can evaluate the sum. It turns out to be 2 to the capital X minus 1. The expected debt is the expected value of that quantity, the expected value of 2 to the x minus 1. And if we try and evaluate that by summing up the values of 2 to the x minus 1 times the probability function, what we discover is that the series we obtain is a divergent series. Indeed, we're adding up the constant 1/2 an infinite number of times, and then subtracting 1. The answer is infinity. This is the expected credit you would require in order to play this game. More credit, of course, than the US government has, or all the governments of the world. Which is to say that indeed you can't guarantee playing this game, that no bank or government would guarantee your credit in such a game. And it's easy to see if you have a finite amount of credit, then you do indeed win $1 most of the time, but with a very small probability, you lose everything up to the maximum level of your credit.